Hey, hey. No, clap to all of you for hacking these last few weeks and looking at big numbers all day long. And yeah, it sounds like everybody's working on some really cool and exciting projects. This is going to be a much higher level than where you guys have been. Maybe like a mental break, like not so many big numbers, specifics about polynomial commitment schemes or anything like that. I'm just a humble product manager. But I think we'll talk quite a bit about how the zkVM works, and maybe there'll be some insights. I'll try to like speed run the slides too. So maybe we can have a conversation. I'm sure all of you are hungry or have better things to do. So we'll go kind of quick. Yeah, I think this idea of unlocking Turing Complete ZK is like a really compelling idea. For many years we've been writing just dedicated ZK circuits, right? And you can think of those as sort of a finite state machine, very limited capabilities, difficult to iterate on. And so I think this is a fun idea to explore. A little bit about me. I've been around crypto for a long time, so late 2014. Don't tell anybody, but I bought XRP, was like the first token I bought. I'm a little embarrassed to say that, but like way back in the day, got really interested in crypto. I learned to code. I'm a mediocre TypeScript developer, but just got like really excited about crypto and like the financial freedom and that it promised. Built a little product called Hashfile, which is a proof of existence. If anybody remembers, it was like sort of like hash a file and post it on chain as like a sort of a timestamp. So that worked on Ethereum, Bitcoin, and XRP ledger. And then I worked for O1 Labs. Do you guys know who O1 Labs is? The company behind Mina Protocol. So they actually were the, fun fact, first team to implement the Halo 2 paper even before the electric coin company had even implemented it yet for Zcash. And so I got to be a PM there on their crypto and protocol teams. And then I heard about RiskZero at DevCon in 2022. And I was kind of like, this is crazy idea. It sounded such an incredible idea. Maybe a bad idea, maybe risky, but really, really exciting idea. And so I really wanted to come work for the company, and I came to work for RiskZero in May of 2023, so about a year and a half ago. Just a few other things, not a cryptographer, not an engineer, I won't pretend to be. I have 4 kids, that's kind of fun. More kids than anybody else in crypto. And then these slides are like very lo-fi. It's just kind of like, you're not supposed to do slides like this. It's quite a bit of text. Normally I have like memes on every page. There's no memes. Just like screenshots of code and some things like that. So a little bit boring. Feel free to ask questions too. Like if you have a question as I'm going, please put your hand up. I prefer to stop and talk about it. I think it makes it more interesting for everybody. Cool. Let's speed run the sort of history up to Turing Complete ZK. So back in 2022, the state of ZK was really interesting. Recursive proof systems were relatively new. Remember at the time, just verifying one proof inside of another was a totally new concept, and that came about in the original Halo paper about 2019. And so in terms of practical proof systems, there weren't a lot that were actually sort of recursive proof systems. Halo 2 paper came out in 2020. And the implementation happened around early 2021. That's around the time that I joined O1 Labs. And O1, like I mentioned earlier, was the first team to actually implement the Halo 2 paper. And I noticed that we were really struggling to maintain our proof system. So we had implemented ground up our own proof system. And the protocol circuits within Mina protocol, it was very hard to find smart people like you all to maintain the circuits. Every time we touched a circuit, we had to touch 10 other things. It was a really core dependency of the protocol. And we were just had very low velocity, and there was lots of maintenance costs to maintaining these proof systems. And really we had 2 engineers that could maintain the proof system. In Mina, there's the recursive proof system is called Pickles, and it was it's written in OCaml, and it's just very difficult to maintain, and only 2 people could do it, and we lost one of those people. So we ended up with 1 engineer who could really maintain our proof system. And yeah, so we were just kind of bogged down, having a really hard time dealing with ZK snarks at the time. One of the other things was our proof system had a really low constraint limit. So the Halo 2 paper, right, it was the first sort of trustless, the first snark without a trusted setup. So it relies on a structured reference string. And so the way that the proof system works in Mina is you can only have up to 2 to the 16th constraints in any given circuit. So that's about 80,000 constraints. It's a very low constraint limit, not enough to do even a single Keccak permutation. And so just again, very sort of bogged down in the technology, hard to build. and moving very slowly. I think a fun anecdote is like the week I heard about RISC-0 was the same week that the Scroll team sort of announced their project at DevCon in 2022. And their goal was building, the first Type 1 ZK EVM with Halo 2. And then, Plonky 2 came out not long after that. Oh, I got a typo. And, proof systems sort of demonstrating proof systems started to get faster, started to use smaller fields. And I have a couple other things on that here. And I would describe this time back then as like finite state machine era. You could really only write relatively simple programs in circuits when describing the polynomial constraints. So I've got a couple examples here, but like, what's the problem with that? The software we rely on today is so complex. If you have to write everything as a polynomial constraint, it can be very difficult to build in ZK. I know the Macy team from PSC, for example, spent years developing their circuits. The Tycho team, writing their circuits for their ZK rollup, they spent years writing the circuits and then threw them away and just began to use general purpose zkVM's. So it's just very difficult to build in this sort of finite state machine era. Code reuse is difficult. So like, for example, if somebody wrote a Rust or a C++ implementation of ECDSA or Ketchak or some crypto primitive, you can't reuse it, right? You have to like rewrite it from scratch. It was a very, very difficult area to be working with the technology. And so when I saw RISC-0, it represented a risky strategy where it was like, proof systems were getting faster, but they were still quite slow. And so this idea of general purpose ZK, many thought was like a crazy idea. It would never work because the proof systems were just too slow. And imagine like, sort of in this era where you're writing circuits, imagine writing a dedicated circuit just to prove that a chessboard has a checkmate on it. Very difficult. Like nobody has written ZK circuits to do that. I think that's a really good example that, sort of working in this paradigm, even doing something as simple as writing a chess engine is quite difficult when you're describing circuits and polynomial constraints. And you can think of too, like the original computers, like a calculator. It was like a dedicated computer, only does one job, addition, multiplication. It only does math. General purpose and sort of Turing Complete ZK has the promise of just helping us build so much faster, so many new fun, interesting things that harness the power of ZK. So that was kind of the state of things back in 2021, 2022. Here's a good example. This is like the ECDSA SIRCOM implementation. Who was the team that did this? I think the Aragon team or somebody like that originally. Oh no, this is part of the 0x Park. I think you can see a link down there. And so, you can imagine this looks, you guys have been looking at things a lot like this for the last couple of weeks, I'm sure, and it's something I'm sure you can read, but, this is 200 lines of code, which doesn't include the circuits for doing the big int multiplications or big int additions, right? There's also many other circuits that this depends on in order to just get quite a simple thing, which is, ECDSA signature verification working. So this is kind of like a picture of what that paradigm looks like, which you guys are familiar with. You step it up from there and you want to build something more complex like a ZK EVM. The Polygon team spent $650 million acquiring ZK teams. The Mir and Hermes teams were like 400 million and 250 million each. They started working on building a Type 1 ZK EVM in 2021. And they just finished it in like February or April of this year. So again, it's like time to develop. There's like 3 years to get a working Type 1 ZK EVM. And the EVM is not all that complicated. There's 140 something opcodes, 10 precompiles, and then you need a bunch of circuits to sort of put all of that together. And so, just like 3 years of development and barely just sort of getting it working, costing hundreds of millions of dollars. This screenshot is just of, this is the SHA-2 precompile written in ZK assembly, like in Plonky 3 in this case. And so again, just kind of like we're just building SHA-2 from scratch again. How many SHA-2 libraries exist in the world? Do we need to write another one? And so sort of the promise of Turing Complete ZK, or we could call it general purpose ZK, is really exciting and compelling. Like, what if we could stop writing all of these like small, these circuits over and over again in different proof systems, and we could just reuse existing code that we know is secure, that we know is audited. That would be really compelling, right? And so to be Turing complete, there's like at least a couple requirements. Number one, you need memory management. So like some notion of memory, the ability to manage it in ZK. You need control flow, and I'm talking about more than just like if statements or regular expressions. Imagine the ability to write a while loop, for example, in ZK. When you're sort of coding a structure that, again, there are some hacks to sort of create control flow, but it's very cumbersome, very difficult to work with. And then I think one of the most difficult challenges in achieving like a Turing Complete ZK system is actually unrestricted computation. Like I mentioned earlier, in Mina's proof system, 2 to the 16th constraint limit, you can kind of stitch those proofs together in perpetuity, but it's very cumbersome to do. And so we would really need to achieve this like sort of ability to do unrestricted compute or unlimited compute. And if we were able to achieve that, a few things would happen. And I think these look like small things at first, but they're very, very powerful. So number one, you could get support for existing programming languages. So instead of people having to learn new languages or writing chess as a set of polynomial constraints, they can use existing tools that they know, and it'll be accessible to many more developers, and you can move much more quickly. That's actually the most important part. And then code reuse. So if you're able to use a general purpose programming language, all of the libraries and implementations and software that's been written in those, open source software written in those languages would then become available for ZK protocols. And so just lots of promise to help the space move much faster and be much more powerful. In order to achieve Turing Complete ZK, though, I think there's like 3 primary challenges, and we're going to get into each of these 3 challenges. Number one, proof systems were too slow at the time. I've kind of mentioned that. There was not a very clear standard to build sort of a general purpose zkVM on. We'll talk about that. And then, again, this problem, like you needed to figure out a way for programs to run indefinitely, which is sort of antithetical or does not work within a fixed circuit, if you will. Not obviously, anyways. So just again, kind of quick recap. So proof systems were too slow. 2018, the Stark paper came out, which was a very nice practical approach to recursion. Cairo used a 252-bit prime field. You started to see like practical recursion, quite performant. Then the Halo 2 paper came out, so now we had Plonk-based recursion. And then Plonky 2 came out in late 2021, and you'll notice that like the fields are getting smaller. So 252 in Cairo. And then Plonky 2 came out and had very fast recursion times, like 300 millisecond recursion times, by sort of targeting this 64-bit Goldilocks field, which had a number of nice characteristics. And even then, so around 2021, when the RISC-0 team started, these were still considered to be sort of too slow to implement general purpose zkVM. And so how did we solve this? Jeremy. Jeremy is our CEO. He's just a math genius, terrific programmer. Him and our other co-founder, Frank, for example, they started an AI compiler company called Vertex that they sold to Intel. He's just been very interested in mathematics and programming for a really long time. Has started many startups in the past. He loves to read math papers in the bathtub. That's like his favorite pastime. And so really like what Jeremy had been doing for many years was implementing proof systems as they came out. So, for example, implementing the original Plonk paper or, like Grot 16. And eventually when Eli Ben-Sasson wrote the Stark paper, he implemented the Stark paper in his own way. And that was the 7th version of this like iteration of proof systems he had been building. And for the first time, he sort of wrote it. That's the way he says he understands it. And he actually was really surprised to see that the performance was like now practical. It was finally becoming practical. But the way he describes it to his friends is all his friends thought there's no way anybody would ever write constraints, that developers would never use it if they had to write constraints. And so he needed to figure out sort of a better abstraction, which we'll get to here in a little while. And so he developed, and this is described in the RISC-0 white paper. If you haven't seen our white paper, I think I'll link to it elsewhere. Our zero Stark proof system, which for the first time used an innovative 31-bit field called Baby Bear. Now the Mersenne field is used in Circle Starks, which is also a 31-bit prime field. But that was the first time we've got down to an even smaller field in which we were able to get really great performance. And what's interesting is despite our proof system now being 2 years old, it's still very, very fast. And so we can prove, because of the ability to parallelize, we can prove the average Ethereum block for mainnet in about 90 seconds. And yeah, it's been around for quite some time. It's been battle tested, lots of development, lots of audits, etc. I don't even remember what that QR code was for. If you guys want to go a little bit deeper on the proof system, I know some people were talking about it. There's a couple links here, the RISC-0 white paper. The dev docs include a nice like Stark by hand tutorial, like literally handwriting out a Stark and how it works. And then this YouTube playlist is also quite nice. If you want to get into the RISC-0 study club. So that's some more resources you guys can go deeper on if you'd like to. And so, and actually this is, one more thing. We've also just recently open sourced Zurgeon, which is our DSL for writing Stark circuits, and our compiler technology as well. One of the things that's kind of fun is we're adding CirComp support. So because like Zurgeon includes a compiler for our circuits, we can actually plug in CirComp R1CS as a front end for our proof system. And you could plug in other front ends potentially as well, like Gnark or Noir, but CirComp is sort of work in progress. That might be a fun like future hackathon or hacker house type project. This is all open source as well. Okay, great. So now we sort of have a fast proof system. It's we have a CUDA prover, and let's assume that the zero Stark proof system is fast enough to support general purpose. There's another problem here, which is, well, what do you build a general purpose zkVM out of? On what standard would you build it on? And so obviously at the time, there were lots of teams building zk EVMs and targeting the EVM. It's great because there's great support within the blockchain space, right? There's like a real valuable problem to solve there by being able to move EVM execution verifiably off chain. The problem is that, again, there's there's no standard library. It's not supported by many software languages, tooling, etc. And so it's kind of like would only sort of be niche to the like blockchain ecosystem overall. I'll also add that like the EVM is changing, so the maintainability is quite difficult. It's not like a set standard. You imagine from between Shanghai and Denkun, you have to change the circuit between the two, and that can be really difficult from a maintenance perspective if you're constantly sort of rewriting your circuit. So EVM didn't seem like the right standard. There's other general purpose instruction set architectures like MIPS, x86. ARM, etc. These have like great tooling, and there's lots of software tooling. They're stable standards. There are some cons though. These are proprietary, what's called an instruction set architecture. So you can't just like use it off without permission. It's all permissioned and requires a license. And then also these instruction set architectures include many instructions. So x86 has about I think 32-bit x86 has about 1,500 instructions. And ARM has about 500. And so remember, if Polygon took 3 years just to support the 140 or however opcodes in the EVM, it would take a long time to get all of that to work in those standards. And Wasm is also like an interesting choice as well. It's open source, has great tooling, great support. The problem is there's like sort of 3 different standard implementations within Wasm that don't match up 100%. And so there's really inconsistent standards. There's also many instructions. I forgot, I don't remember what the count is, but I think it's hundreds. And so that also didn't make it a great fit for ZK. And so, Jeremy and our co-founders they were working at Intel at the time, and we're very aware of RISC-V, this MIT-based open source instruction set architecture. And this actually looked like a really great fit to deliver on general purpose ZK. So it's an open source ISA. It works like 32-bit instructions work well with a 31-bit field. There's only 72 instructions in the standard. I think that's the number. And there was quite a bit of momentum in terms of like tooling, like good support in Rust, C++, etc. The drawback at the time was it was quite an early standard, so not a lot of tooling. There's lack of Go support. Go doesn't compile the RISC RV32IM, for example. And there wasn't a lot of Rust tooling in particular within the Ethereum and like crypto ecosystem. Or just let's say the blockchain ecosystem overall. There was lots of like Go and C++ and other languages, but not a lot of Rust in particular, which is sort of the best language that we landed on. And so Rust or RV32IM ended up being sort of our solution to this issue of sort of a lack of general purpose standards to build on. And in hindsight, it turns out to be a really great decision. Obviously, there's many sort of like follow-on zkVMs. The Velita team, they had their own ISA, but now they're also supporting Rust code. Obviously, the Succinct team is using the same standard. Nexus VM. There's many more that are all now using RISC-V and some, or at least Rust in some form or another. Some Rust compiled down to some ISA. And then there's many. I think zkM is also targeting RV32IM, etc. It's interesting. I think we've been so successful in sort of promoting this as a standard for general purpose ZK. I'm not sure if you all have seen this, but this verified zkVM initiative by the Ethereum Foundation, they're spending about $50 million to formally verify 2 ZK EVMs, which I think will be RISC-0 and Succinct's SP1 or something like that. So anyways, even the Ethereum Foundation is saying the future of ZK EVMs is actually in general purpose RISC-V VMs. If you visit that website, you can kind of see some more specifics. And so really, today, where we're at today, RISC-V is very much becoming sort of a standard for general purpose ZK VMs. I went a little too far. Okay, and then so this last problem of indefinite runtimes. How do you run a program in ZK indefinitely, with sort of unbounded runtime? It's a very, very tricky problem, and it's really necessary though, right? Because you can, if you want to run a general purpose program in ZK, the inputs may determine how long it runs. I could maybe enter like an if statement that quickly exits the program, or maybe I enter like a while loop that runs indefinitely. So it's quite a tricky problem that's not sort of obvious to solve with just like an individual circuit. And so a couple other, let's see. Yeah, and what's really interesting about this as well is blockchains, how blockchains have solved this problem is by enforcing a cap on the computation. So like, for example, metering via gas on Ethereum, right? Has sort of solved this problem just by saying, oh no, you can't do unbounded computation. You can only do 15 million gas is what we target with a max of 30 million per block or something like that, which are the limits within Ethereum's case. And so you can imagine that if we could break those limits, like remove the scarcity of execution, you could do lots more innovation. Like imagine if you could run inference on chain or something like that. And so this idea of being able to like break this limit was very, very compelling and very exciting. And so we needed something to enable this. And in RISC-0, we developed a system which was the first of its kind, called continuations. There we go. To-do diagram, I like that. And so continuations was a really interesting, and there is a diagram after this that I'll show you. But it was a really interesting insight, which is you can use 2 circuits to achieve unbounded computation. You can have one that proves like sort of a set of RISC-V instructions, and you can have a second recursion circuit which stitches those RISC-V execution proofs together in sequence, so that you can prove a computation in perpetuity. I'm just going to go ahead and get right to the diagram, and I think we can spend some time on this, and I'll just this is a diagram that sort of explains how the zkVM works, and I'll just sort of run you through these like 4 primary stages of what makes the zkVM possible. So the first step in like the zkVM is something called execution, and this is a single-threaded process. It's not parallelizable, where you imagine you've written a Rust program and compiled it down into an ELF, and you take that ELF and you take the inputs to the proof, and you put those together, and in execution, we just execute your program. We just run your program, and the executor also makes some polynomial commitments. You can imagine that it's like sort of chunking up the instructions and making commitments between the sort of barriers between these chunks of execution. So you can see like if this was like your program, there's maybe like chunk number 1, chunk number 2, chunk number 3. It's just making polynomial commitments between these different chunks, essentially, just sort of running your program. And this is a single-threaded process. Once we have that, you can think of these like inputs to the prover. We next have like our RISC-V circuit. And that RISC-V circuit takes a chunk of RISC-V instructions and proves them individually. And this is a Stark-based prover. This is all Starks. I'll talk about Stark to Snark over here. And so what's really interesting is like in our proof system, this is like nuanced detail, but your program actually has a memory argument in the circuit for each individual segment. And so that means that you can actually start proving that segment as soon as the execution is complete. Succinct actually went a different approach. They have one memory argument for the entire execution trace. And so that means you have to like completely finish execution before you can start any proving. And so that's just like a little trick that we have so that you can start proving for big proofs like before execution is even complete. And so after we've done execution, we've sort of chunked up the instructions into different potential subproofs or inputs, if you will. Actually, one more thing about this. This is configurable in our proof system. It's called like the PO2. The power of 2 size is how many instructions you want per segment proof. We call these like individual proofs that these are going to help generate. We call them segment proofs. And so you can actually configure how many instructions are in one of these individual segment proofs based off of a power of 2. The default is like 2 to the 20th. So about 1 million RISC-V instructions per segment proof. You can go up to 2 to the 21st, so like 2 million. Or you can go down to like, I think 2 to the 16 or something like that. And so what's interesting is that actually drives the memory requirement for the prover. So less instructions means less memory. So I want to say that at about 2 to the 20 instructions, like 1 million instructions per segment proof, about, I want to say 13 gigabytes of memory are required, as an example. If we lower the PO2, I think we can get all the way down to 16 or 17, and it just requires hundreds of megabytes of memory. So you can actually generate these proofs, albeit a little bit slowly, like on small devices. Many times ZK systems like the Polygon CDK or zkEVM prover, for example, requires like almost a terabyte of memory. This is actually quite like a memory-friendly approach because we can like limit the size of each of these segment proofs or configure it, if you will. OK, so that's step number 1, execution. And so once we've sort of prepared the inputs for the RISC-V prover, these like step 1 of your execution, step 2, step 3, they run through the RISC-V prover. This is a parallelizable process. So you can generate all of these proofs in parallel. Like if you have 300 segments, or as an example, the average Ethereum block on mainnet is about 2,200 segments with a PO2 of 2020. So it's like 2.2 billion RISC-V cycles roughly to prove the average Ethereum block. Well, if you had 2,200 machines, you could parallelize like the proving of all of those leaf proofs. And actually, there's some tricks to get the number of machines down even further, but I'll skip that for now. And so we run those segments through the RISC-V prover, and we end up with what's called a segment receipt. And this is like just like a Stark proof. It's about 300 kilobytes. And you can imagine that this is like step 1 of your execution, step 2, step 3, step 4, et cetera. But now we just have all of these leaf proofs, and we want to get to like a succinct proof. And so the second circuit we have is our recursion circuit. And what the recursion circuit does is just very efficiently verify all of these segment proofs. And so we end up sort of merging these. We want to merge these into a single root using this recursion circuit. The times on this, like just as an example, like on a 4090 GPU, this step takes it runs at about 1.5 megahertz, which is like a 1.5 million instructions per second. So this step can run in about 1.5 to 2 seconds on a 4090. This step here takes about a second to run, a little bit less than a second. There's actually like 2 rounds of recursion that happen, just to give you guys some numbers. And so we take all of these Starks and we just sort of in a binary tree, right? We start to merge them down until we get to a single succinct Stark. So in this case, we have 6 leaf proofs, and we have to do like 1, 2, 3 rounds of recursion in order to achieve a succinct proof. And what this recursion circuit is doing is stitching them together in order, right? It's saying like 1 and 2 here, and then this is saying 2 and 3, and then this does the same thing, sort of a range proof, or to merge these together. So now we have a Stark at the end, a succinct Stark, which is 300 kilobytes and represents a proof of the full execution trace of your program. The problem is these Starks are, like I said, 330 kilobytes, something like that. It would cost millions of gas to verify on Ethereum, which is really not very practical. And so in our proof system, and there are many other teams taking this approach now as well, we, from the constraints of our recursion circuit, we generate a SIRCOM circuit that verifies our Stark proofs, which effectively allows it to act as a wrapper. One of the things that's really interesting about this is what you'll notice is because the Grot16 circuit is verifying a recursion proof, that means you only need one verifier contract on chain to verify all zkVM programs. In Succinct in the past, they're now taking the same approach, but in the past, in their version 3, but in the past, you had to have different verifier circuits and things like that. You had to do new trusted setups if they did a new release and change their circuit. This means we can actually change the RISC-V circuit and not have to deploy new verifier contracts, because as long as the recursion circuit stays stable. And so this is like a really nice trick to help with the maintainability of on-chain ZK systems as well. And so this Grot16 circuit generates a small, like 300-byte Grot16 proof that costs about 260,000 gas to verify on-chain. This process, like running on a GPU, takes about 12 to 15 seconds, something like that. Currently, the Circum, like the Rapid Snark Prover, is the fastest one. And actually, we can't do this on GPU. It's CPU bound because there's some handwritten like x86 instructions. So we actually can't generate this on a GPU right now. That's something that we'll be able to do here quite soon. But we think that that'll get down to quite low times as well. And so to use an example, just to give you guys some more numbers, this step runs at about 25 to 40 megahertz. So we can execute at about 25 million to 40 million instructions per second. And we know we can make that quite faster. And so the executor actually represents like our upper bound for performance. So because we can execute at 25 megahertz, or let's call it 30 megahertz, we can start up the provers like as soon as the segments are done. And so we can actually we can almost keep up with that 35 megahertz. So that's about our theoretical limit right now on proving throughput. And that means the last that we shared on Twitter was like we generated a proof with the Tycho team of a block in 90 seconds. And this was, by the way, like the average size block, not just like an empty block. This is like a real block. But now we've done a couple updates, and our next release will probably have that time closer to about 60 seconds to prove the average Ethereum block. Cool. Does anybody have any questions on that, on the zkVM and sort of how it works, the concept? Yes? Yeah. So continuations is just this trick of using the recursion circuit so that you can just keep sort of proving. You can imagine that you could keep adding leaf proofs here, and you could just keep going in perpetuity. So it's really like the split of the RISC-V circuit and the recursion circuit so that you can stitch them together in sequence. So really all of this, like the commitments between the segments here, and then the inclusion of the recursion circuit is what makes continuations possible.
Can I ask a question that's in the RNSCV proving, that's kind of, they have like index and you can find each prover. If you got something wrong, you can find it.
Oh, can you find if something went wrong here? Is that what you're saying? I'm not sure, like what would be an example of something going wrong?
If that one kind of the thing that you can find it is got something wrong, you can find it because it is like it's kind of like index, or you can find which one is not the correct, or the prover process is wrong or something.
Yeah, what's interesting is if something broke, it won't verify in the recursion circuit. Because we've made like the commitments up front that this proof will not verify if something breaks. So it sort of has to work or it won't, one or the other. There is like maybe like a machine dies or something like that. Like imagine you're proving all of these 6 leaf segment proofs on different machines. Maybe this machine dies or something like that. You have to like restart the proof, but like you can't, if you could generate an incorrect proof, there would be no soundness in the proof system. Any other questions?
So, what's the challenge if you want to do some parallel program?
What if you want to do a parallel program?
Yeah, like so the execution, we have the single thread, right?
Yes.
Yeah, so if we have multiple single threads, so what's the challenge?
Oh, to be able to do so. And I don't know if I understand your question entirely, but this is single threaded, like I mentioned, right? This is all parallelizable. If you want to run like a multi-threaded process, is that what you mean? Like in your RISC? Yeah, it's not really supported. Like you get parallelization even if the program is single threaded. There's not really a reason to run like write your program as a multi-threaded process, if that makes sense. And by the way, like the way that this works too, the way you compile down to like our RISC-V standard is the Rust project itself. There's a target triple for us where you can, when you're in Rust, you say, I want to compile down to RISC-0. So that's something that's been merged into the official Rust project. It's like we have our own sort of build target within the Rust ecosystem. Any other questions? All right, let's see what else I have for you. Okay, so we came up with a system, and now we really, we've really unlocked general purpose. I'm not kidding when I say that development times are 100x faster or more. Just as an example, like I showed you before, like the SHA-2 precompile in the ZK assembly. It's quite easy to do SHA-2 in the zkVM, right? Like we bring in this module from the RISC-0 zkVM crate, and we just write regular Rust to do a SHA. You don't. And by the way, this like is based off of the existing like Rust crypto library is the SHA-2 function there. And so you imagine now it's like much easier to just we don't write polynomial constraints anymore. What's really interesting is you can actually, for example, take the Rust verifier for a different proof system, and you can verify it in the zkVM, and the performance is actually quite good. There's teams building aggregators that verify Plonk and Grot16 and SP1 inside of RISC-0 and RISC-0 inside of SP1, et cetera. So you just end up with like, imagine if you had to handwrite those circuits to verify one proof system inside of another, it would take a really, really long time. So we can just move much faster. These systems are also, and actually just as an example, today like we run a nightly job, and 70% of the top 1,000 crates, I put 100, but the top 1,000 crates just build within the zkVM, no issues. When you're in the zkVM, you can imagine it's kind of like its own OS. There's no file system. There's no time. You can't read time, and you don't want to call for randomness within the zkVM. You actually can call for randomness, but you don't want to. And so you can imagine there's like some syscalls that might be available in a typical OS that aren't available in the zkVM. Just sort of a fun anecdote as well. There's actually like in that RISC-V circuit, there's actually a 256 megabyte memory limit within the RISC-V circuit. So you actually have like heap and stack memory within the zkVM. Only 192 megabytes are accessible. There's some stuff in the first 64 megabytes, but there's actually memory within the zkVM. And you can sort of think of that as like intermittent state, right? It's actually a very powerful concept because now you can actually like manage memory inside of ZK. You end up with much more auditable systems. Imagine like if you build something on the zkVM, you're just reading regular code. You're not reading math. It's much easier to sort of make sure there's not a mistake. There's a lot more firms that are good at like sort of reading regular code rather than ZK code and making sure these systems are safe. It's so much more maintainable. So you imagine, somebody just mentioned to me that we haven't updated Zeth in a long time, so maybe this isn't the best example. We're actually updating it right now. But when Zeth was like our ZK EVM prover, so imagine we built the ZK VM last year. One of the first things we did was take the Rust Ethereum implementation and put it into the ZK VM. And what you got was a ZK EVM inside of the ZK VM. And you imagine that all you have to do, say you build that, a new version of Reth comes out, for some new hard fork, let's say the next hard fork that's coming up, we can just kind of, it's much more traditional software updates. We need to update Reth inside of our guest program. The guest is sort of where you write your ZK logic in the ZK VM. So you just sort of update Reth, and voila, you have like an updated ZK EVM. We don't have to go back into the constraints, like write new opcodes, update, elaborate dependencies, et cetera. These are much more maintainable systems. And so there's just all kinds of new use cases that this unlocks. A couple fun ones, like ZK Lite clients are just like becoming more and more rampant because you can just, again, take some Rust crates, put it in the ZK VM, and generate proofs of consensus for various Lite client protocols. Another one is like alternative VMs are now popping up. So though Polygon spent 600 million just trying to write one ZK EVM circuit, now any team can, for example, like pull in the Solana virtual machine implementation and generate a ZK SVM inside the ZK VM. So you're seeing that from teams like Hashflow. They're building something called Exchange OS on our ZK VM, where it's actually a very small state transition function specifically for an exchange. Just make sure that the person has the right liquidity. It's not elaborate like the EVM or general purpose. It just does sort of a very small set of functions, checks some signatures, things like that. Eclipse is using the SVM inside the zkVM. They intend to build ZK fraud proofs with it. And then Cartesi is like sort of like a Linux-based project that is working on ZK fraud proofs just over generic Linux programs as well. Some fun examples we've built. I didn't include links, but you got to see if you can make Doom run, right? And we recently ran Doom in the zkVM. And even like one of the original Game Boy Pokemon games, including rendering. That's the fun thing. We actually like proved the rendering in that process as well. And one of the examples, let's see, I'll just keep moving on. And so I said earlier, like, imagine writing a set of constraints to prove that there's a checkmate on a chessboard. It would be quite difficult. This is our chess example. It's in the repo. It's really, what is that, 15 to 31? It's about like 16 lines of code to prove that there's a checkmate on a chessboard. And all we did was pull in this checkmatey crate, which is sort of a chess engine for that's written in Rust. And voila, we can have like provable games like chess. Another example, I mentioned Zeth. Zeth was our ZK. So about August of last year, actually when I joined the company in May of 2023, we were proving one single transaction execution in the Revum crate. And my mind like exploded, like just one transaction. I was like, wow, we can already prove execution of the Ethereum virtual machine. This is amazing. And so in August, we built Zeth, which was the first type 1 ZK EVM. And we built it with like 2 developers in 3 weeks. We had a working prototype. So whereas Polygon had been spending 2-3 years at the time and still didn't have a type 1 ZK EVM, the power of general purpose like let us just move so fast. Again, performance was a concern at the time, but I think this is a really interesting statistic. We sampled a bunch of blocks. The average fee was almost $1,700 in fees in those blocks. We can generate a zero-knowledge proof of those blocks for well less than $1 today. And so imagine that ZK is really like unbounding the execution limits. Like right now, execution is very scarce because it's coupled with consensus. And so you have these limits on blockchains on how much execution you can do. And ZK is just going to completely like remove the limits of execution. So that was this is for fun. This is not the complete implementation of Zeth, but this is like one of the main guest programs. And you can see that it's only like 50 lines of code. And actually, this is the question that you asked me earlier, why don't we update it? This is the updated version. It's simpler. The original one was actually quite a bit more elaborate. Another really cool thing you can do, and here's the QR code to get to Steal if you want, but whereas Zeth proves whole blocks at a time, we wrote a library called Steal that lets you execute any smart contract off-chain. So instead of like full blocks, you can actually query from an RPC provider a smart contract. We do the ABI decoding in the zkVM. We do all of the Merkleization and sort of can generate a proof of that smart contract running off-chain. Obviously, you can't do like S stores. You can't save. That has to happen on-chain. But really, every other opcode you can execute off-chain in this way. It's a really powerful library. So you can actually, let's see, which one was this? This is a cool example. So yeah, this is like Solidity, but with off-chain execution. So you can just write your contract in Solidity and call it off-chain in the zkVM. If you're like familiar with the ZK, or excuse me, if you're familiar with the EVM, you may have this thought, which is like, what if the RPC provider provides you the wrong smart contract? And there's actually a way that we solve that in Steal called Steal commitments, where we actually commit to the block header at which you're executing the smart contract, and that commitment is checked on chain. So these are like full validity proofs of arbitrary smart contract execution off chain. This is fun because one of the things we can actually do with Steal as well is we can actually go back in time on the beacon chain. So we can go back an epoch at a time to prove something about historical Ethereum state even. So this is just like sort of a really fun new thing that would not have been possible without general purpose ZK. Highly recommend that library. And then I thought at an Ant Alpha Hacker House, it'd be fun to just mention, there's work in progress right now too to be able to verify risk zero proofs on Bitcoin using the BitVM or BitVM2 protocol. This will get merged into the BitVM repo, but this is work in progress right now. And so this is actually a library that makes it possible to verify, and there's a QR code to it if you want to check it out, but to verify our zkVM proofs on Bitcoin itself so that you can build trustless bridges for Bitcoin. That's what Citrea and a number of other teams are working on as well. Cool. Last thing I'll mention, we're building a protocol called Boundless. You all might have heard of it. The zkVM solved this sort of writing circuits is painful problem. We've made it fast now, so proving is actually quite inexpensive, like I showed. Now we have one circuit to maintain a verifier contract on chain, so this problem's quite relieved. And then running provers is quite we've gotten very good at that, and we've written some terrific software for that. But ZK is really hard. How do you integrate it into your blockchain protocol? How do you pay for the proofs? If a user wants to process a transaction that's reliant on a zero-knowledge proof, how do they facilitate the payment for that? It's actually a very difficult problem. Verification is still quite expensive. 300,000 gas to verify a Grout 16 proof is about $10, depending on gas prices, but about $10 on average. And this is a really interesting one. Proofs, ZKPs are inherently verifiable. You can't fake or generate a fraudulent one. If you can, then the proof system's broken. But centralized provers do introduce liveness and censorship issues. So you imagine that if you build a dApp on chain that relies on zero-knowledge proofs, and let's say it's a rollup, actually, and say that rollup is paying AWS with a credit card for their proving. What happens if the company goes out of business, or what if AWS goes down, et cetera? There's actually many liveness concerns that come along with adopting ZK and being reliant on a centralized prover. And so yeah, we're building this protocol called Boundless. What is it? We call it a universal ZK protocol. So it's a set of standards for verifiable execution. You can think the zkVM is sort of in this set of standards here. We will be able to support other zkVMs in this protocol in the future. There's sort of standards for order matching. You have a user who requires a proof to process a transaction. How do they sort of match with the prover, and what does that process look like? Coordination of the provers itself. So the node implementation for Boundless includes a system called Bento for parallelizing the generation of the proofs and doing that really efficiently. There's standards for aggregation, so smart contract interfaces and things to provide some standards around aggregation. And then for settlement, how do you sort of settle this proof and exchange payment at the same time? On which chains can you do that on, et cetera? And the last one that's kind of exciting is there's also sort of a layer in the stack, if you will, for incentivizing the proving itself. That's not something we've revealed yet. I'll just tease it, and probably sometime early in the year we'll share more about that. This is actually an open protocol anybody can build in. So for example, Electron is building an aggregation service. There's lots of teams building applications and various developer tooling on top of it as well. Even we're talking Snarkify, for example, plans to run a distributed prover within Boundless. And so you can think from here, you can build prover pools, and anybody can sort of come and participate at any place within the protocol. We're also building our own implementation of each of these things. So there's a market, like I mentioned, for matching buyers and sellers of proofs. The node does all of the prover coordination and proof coordination. There's a set aggregator contract that provides a standard for proof aggregation and how you can batch proofs and verify them on chain. And then there's various verifier and market contracts to facilitate the settlement. Just kind of what we're hoping to achieve with Boundless. You can imagine this is an example of some different parameters within just Ethereum and Solana, but you can imagine other chains being added here. And these chains have to set quite low execution limits for their transactions in order for consensus to happen fast enough. And so you can see here that Solana has a very fast block frequency. It's 600 milliseconds. It's under a second. And so in order to have very fast blocks, you have to have very low limits on how much compute can go into an individual transaction. And you can see with ZK, if we're able to add the power of ZK to Solana, you can have unlimited execution within a really fast sort of settlement scheme. And so we really just plan to enable every chain to have the power of ZK. There is obviously you have to verify the proofs, so there's a little bit of execution that needs to happen within consensus itself, but we think this is a really powerful protocol that gives every chain the power of unlimited computation in ZK. That's it. I'm happy to take questions. We did set up a RISC-0 developer telegram if you wanted to jump into it. Yeah, thank you all for your time. Thank you. Does anybody have questions? More questions? No? Yeah.
The cost you mentioned in earlier slide is the verification cost.
This one here?
Earlier, yeah, this one.
Yeah.
Is there a verification cost?
No, this is just cost of execution only. This does not include verification costs, yes.
How do you measure this cost?
Yeah, so this is the cost to run the hardware to generate a proof of this block. Does that make sense? Like, such as AWS, yeah, exactly, yeah. Yeah, so you would like pay AWS $1 to generate a proof of that whole block. Yeah. It's a good question. All right, thank you, yeah.
How can I find details regarding boundless?
Yeah.
Is there any code available for that? Or?
Yeah, we've been a little bit coy. Nothing's public yet. We will have our first, so we've done 2 test nets so far, just like sort of an internal dev net, and we just wrapped up a permission test net with like 10 third-party provers and like 10 application developers and rollups. And you know, we're the team at Succinct is great. We want to like, you know, we've got a lot of competition in the space. We're just kind of keeping it a little bit private right now. In early December, we plan to open up the code base and make it available to everybody. Proving will likely open up to any third-party prover around January, something like that. And what's really exciting about Boundless is it is fully decentralized. So you know, some of the other prover networks, if you will, are actually just centralized coordination services. There's no decentralization whatsoever. And so from day one, Boundless will be a fully decentralized protocol that you can run entirely on-chain if you'd like. And then there's some off-chain infrastructure to save gas as well. Sorry, I'm like hand waving a little bit. But actually, and at bboundless.xyz, it's like this. Yeah, that's the one. There's like a blog post and some minor details, but there's no code yet. All right. Any other questions? Thank you for your time, everybody. I hope the Hacker House has been good.